right, we're going to get started with Recitation Guide Week 3. So I think we can kind of say that you guys are pretty familiar with what's going on in terms of these three intermolecular forces, so I'm not going to draw them in this one. Instead, what I am going to draw is a picture of two molecules or ions exhibiting each of the following types in terms of an ion dipole, because this is one that's new for us this week, and then I'll go through the others during recitation. So with an ion dipole, we're basically looking for two things. We're looking for an ion, and then we're looking for a dipole. From dipoles, we know from dipole dipole and also hydrogen bonds, which are a special type of dipole dipole, and that we're looking for something that has a difference in electronegativity. Otherwise, it's not doing much for us. And so when I think of something that has a difference in electronegativity, something we can think of is something like ammonia that has dipole dipole in it. It also has hydrogen bonds. Something that doesn't have hydrogen bonds but has dipole dipole is something like formaldehyde, which is that great carbon double bound to an oxygen that has then those 4 lone pairs on the outside, and then that carbon, to be perfectly happy, has 2 hydrogens attached, something like that. And when I think of that then being attracted to something like, let's say, a Ca2+, like a calcium 2+ ion, this in itself is an ion dipole. So if you ever show something that, say, has an ion, usually something positive is pretty good, and then something that is a molecule that per se has this sort of electronegative end that's then attached to, say, an electropositive end, then we're in business here. That's when we know that we're showing an ion dipole. Okay? Next up, we're going to rank the following intermolecular forces based on relative strength. I'm going to go with my gut instinct that you guys remember that dispersion is the least, and that's just because, again, it's between everything. So everything has a dispersion force, and that's what makes it so, in this terms, weak, because it's something that is experienced even within molecules within themselves. So it's a very weak force. So this one we're going to rank as like number 4, like the weakest. Next, I'm going to go dipole dipole. The reason I'm going to say dipole dipole is, again, we're now talking about electronegativity. So besides dispersion, it's the overall negativity within its own self, but also between other things. We're now moving on to something that actually has an electronegative difference. And so that's going to actually be more attractive, right? We have something that's a bit more positive now and something that's a bit more negative, and they're going to be a bit more attracted to each other. So this is going to be 3. Now, the reason why hydrogen bonding now is ranked at number 2 and is stronger than dipole dipole is, again, we have hydrogen, which is probably the least electronegative thing, unless otherwise bound to something that is super electropositive, which in the cases that you were going to look at is not the case. And it's always got to be bound, though, to something that's super electronegative, so it rules out any exceptions. Things like fluorine, oxygen, and nitrogen. These are the most electronegative elements, and when hydrogen is bound to it, it becomes super electropositive. And so it becomes an even stronger dipole dipole. That's why it has its own set class and category, and that's going to come in at number 2. But again, a hydrogen bond is still essentially a dipole dipole interaction. It's just one of the strongest dipole dipoles that we know. And so that's why an ion dipole now is going to trump that. And the reason for that being now is the ion is literally specifically positive. It's no longer going to be something that, due to a bond to something else, it is positive, like hydrogen, or like any other dipole dipole that you've seen, like the formaldehyde up here. But instead, what we're getting at is that something that is innately positive, something like that calcium that always has a positive on it, something like sodium that always has positives on it, rubidium, things that are in group 1 and group 2, those usually are innately positive, especially when in a bond. And so that one's going to be always positive, and that means it's going to be a lot stronger because it's going to have that super positive charge seriously attracting the negative charge. Now, in order for a liquid to boil, to go from liquid phase to the gas phase, what has to be overcome? And I think, with the theme of this week, we can all see that it must be intermolecular forces. So that's what has to be overcome to get something to boil. So how would stronger intermolecular forces now affect the boiling point? Well, this is us really diving into what does it mean when we say we're having to overcome intermolecular forces. And what that means is that if something is more strongly bound together, it is harder to pull apart. We're really having to put in a lot of energy, and in this case, heat energy. And by heat energy, I mean that we're causing these molecules to bounce around, and then we're slowly just like, okay, and then they break apart. But if I have to put in more heat to make them vibrate more to break apart, that in itself means that it's going to have a higher boiling point if it has a stronger force. Because otherwise, if I have a weak vibrating energy, they're just going to vibrate like this. And they're not going to really fall apart. But if I really vibrate them, but that means I'm really racking up the heat, aka increasing that boiling temperature, then that means it's probably a stronger intermolecular force. So that's why strong intermolecular forces would drive up that boiling point. All right, so describe what surfactants are and how they impact the surface tension of a liquid. So when I think of surfactants, I automatically think of something like soap, because those are things that I use to wash my hands. And I don't know if you've ever seen soap with water, but it creates those bubbles. And that in itself is what surfactants usually do. In chemistry, we use them a lot in HPLCs, or high pressure liquid chromatography, something that if you're in pharmacy, you're going to see a lot. If you're, say, doing, your good old accounting here, again, soap is a great thing to think of. How do I keep myself clean, especially in a pandemic? And essentially what you're going to have is a super hydrophilic head and a super hydrophobic tail. And these things are going to create a sort of barrier, because those hydrophobic tails want nothing to do with your water. So they're all going to pop out of the top side of the water and rest on the top. But if you have all that hydrophobic part sitting on the surface of that water, it's going to make the water break apart, because it's disrupting the water interacting with other water molecules, right? Because the thing that gives water such great surface tension is the hydrogen bonds it has with itself. But if you have these hydrophobic tails deciding to break those bonds apart, you're suddenly losing surface tension. So if I were to take away this beaker and I had it full of a surfactant-y water, that water would splay out really flat instead of that nice little bubble that we normally see with water. Okay? For the two applications, we're going to go through that in lecture. You're going to go through it in lecture as it says, but we're also going to discuss in recitation. So I'm going to skip over that for now. Now, adding a salt to pure water increases the boiling point. Let's use our understanding. Well, if we go back to the top of this page, you and I already said ion dipole is number one, right? That's the strongest. And we talked about how its stronger intermolecular forces affect the boiling point. We said the stronger the intermolecular force, the higher the boiling point. So I'm going to give a full answer in recitation, but kind of refer back to questions 3 and 2 when thinking about number 5, okay? All right, now moving on to number 6. Intermolecular forces impact physical properties of compounds such as vapor pressure, boiling point, melting point, surface tension, and viscosity. Now, sorry, I got a phone call. Okay, so when you have something that's a strong intermolecular force, you've got to think, okay, again, like we were talking about with boiling point, things are super duper strong. So we're going to have, a strong intermolecular force would mean a high boiling point, right? Because we've just established that it would take a lot of energy. And also a melting point, which are, again, putting in a lot of energy to break bonds apart. Now when we think about vapor pressure, if I have a very strong molecular force, it means it's not going to boil very easily, as we've just kind of highlighted here. And vapor is essentially liquid to gas. And if something is going from liquid to gas easily, then that means it has a low boiling point. And so, opposite to a high boiling point is low vapor pressure. And if we have low vapor pressure, we can only assume that because we have strong intermolecular forces, it's having a tougher time breaking apart, becoming a gas, and in that means that it's going to have a low vapor pressure. So then when we move to surface tension, I like to always think of water as my go-to thing here, but because it has hydrogen bonding, because of that, it's going to have a really high surface tension. And that's when I think, okay, but hydrogen bonding is also considered a pretty strong intermolecular force. It's the strongest dipole force. And so with that, I can say with pretty good confidence then that if it's going to have a strong intermolecular force, it's going to be really hard to break apart that cohesion, that cohesive force that keeps it at tension on the surface. And then when I think about viscosity again, if I have a strong intermolecular force, super duper strong, it's going to be really viscous, because viscous materials are things that don't move very quickly because they're so attracted to each other, because they enjoy each other much more. And so when I think of something that's super viscous, like honey, oil, things like that are really thick, those things all have very strong intermolecular forces. So I'm going to go with high viscosities as well. All right. Now we're going to go through half of these now and half later. So I'm going to do A, and then I'm going to do C, and then we're going to go through B and D in recitation. So A, boiling a liquid is an endothermic process. So when we think of boiling something, we're thinking that we are putting in heat, and the water molecules are absorbing heat. And whenever I think absorbing heat, I automatically think of an endothermic process. And so with that, I'm definitely going to say that A, boiling a liquid is an endothermic process, is more than definitely true. And then when I look at C, molecules in the gas phase move with greater speed and freedom than in the liquid phase. This is something that I have to take back, because liquid and gas both are something that move to the shape of their container, right? I have water in this water bottle. If I turn it this way, the water does not suddenly disappear. It forms to the shape of this water bottle. With that being said, gas in that container would do the same thing. The only difference is if I were to squeeze that container close, think of like a balloon animal. It takes the shape of that balloon animal, right? The gas does. Water would have a difficult time doing that, because water is not easily compressed or expanded. In fact, it's not, because technically if I were to squeeze around water in a balloon animal, I would have a tough time making it, because the water would not be compressed very easily and would not go into the expanded parts as easily either. Well, when we see a balloon animal, it's normally filled with air for that very reason. It can be compressed and expanded into different paces. And so that's why this one will have greater speed and freedom than in the liquid phase. So this is also true. Okay, finally I'm going to do half of these as well. I'm going to do this one and this one. So identify the total number of ions per substance. So I count 1 and 2. So I've got 2 total. That one should be kind of easy to see because we got the split here. Then when we move on to barium hydroxide, I've had a lot of people say 2 before, and I can see why. And I split this up. I see 2 things. This is 1. The thing to remember is I have 2 here, so there's 2 hydroxides here. I've also had people say 5, and I can see where you would think that. You've got 2 oxygens, 2 hydrogens, but we're talking about ions here, not molecules. Right? So if we're talking about ions, I just want to know the ions, not necessarily each individual piece. And so in this case, I'm just looking at this hydroxide ion, and in that case, I have now 3. All right, and then finally, we're going to do half of this equation. We're going to do the Ca2 plus part now. When I think of the concentration of ions in a 0.255 molar calcium chloride solution, what's the molarity, or the concentration? Because remember, molarity is concentration. These are basically synonymous. In Ca2 plus and Cl minus. So again, since we're finding out moles per liter, pretty good for me to write that 0.255 moles per liter is exactly what we're talking about when we talk about molarity. So I know that I'm basically just needing to go from moles of one to moles of the other, because the liquid, or the 1 liter, is already in the denominator. And so this right here is for calcium chloride. And I just need to remember that for calcium chloride, essentially, that I'm going from calcium chloride that is going to break down itself into 3 ions, as we were doing above, right? So I'm going to break this down, and I'm going to get 1 ion of Ca2 plus, and then I'm going to get 2 ions of my Cl minus. So when I'm going to transform this, I just have to cancel out my moles. So I'm going to have 1 mole of my Cl, or my calcium, Ca2 plus, and that is going to equate to 1 mole, because we can see how they're 1 and 1 here, 1-to-1 mole ratio of my calcium chloride here. And so then these cancel, and I cancel these out and cancel these out. And so then it's just 0.255 times 1 mole of calcium of calcium ion, and so that means that the concentration here must be 0.255 calcium ion per 1 liter, because that's still left in my denominator. So my molarity for my calcium ions is going to be 0.255. Later in class, we're going to go through how we would get through Cl-. Alright guys, thank you so much, and I will see you next week.